Structure and bonding. Now, in the first two chapters, we've seen the structure of an atom. We have seen the various elements and also classified them into families. Now, from these two chapters, we can be able now to explain why substance A is more reactive than substance B. Now, in this chapter, we are going to look at something different but quite related to what we have seen in the last two chapters. Now, you're obviously familiar with very many chemicals and other substances in the material world. From the dreaded corrosive and highly reactive acids, the harmless water and the moderately reactive chemicals, the very precious and expensive diamond and the not so good looking charcoal, the choking and irritating ammonia gas and the brown nitrogen peroxide gas, amongst many others. Now, what we want to see here is at the very atomic and molecular levels, how do these substances look like? How are the atoms we've studied so far arranged to make up these substances? Now, you will see that different arrangement of the same type of atoms can result in totally different materials. Now, it won't surprise you therefore that actually that very beautiful diamond is composed of the same type of atoms as the dirty charcoal. Now, the knowledge on structure and bonding is actually very important in understanding the physical properties of the various substances, be it conductivity, melting and boiling points, softness and hardness, and general appearance. Yet, for the most part, it could pose as a stubborn topic among some students. Mostly, students are not able to distinguish between bonds, structures, and mostly the intermolecular forces when it comes to molecular compounds. Now, I will try my best to explain it in a simple but very inclusive manner, but you must also promise not to get confused, and that's a deal. So let's do this. Chemical bonds. When atoms combine during chemical reactions, a mutual force of attraction develops between them. This force holds the particles together and is called a chemical bond. The bond holds the particles together in a regular pattern called a structure. Remember, atoms are composed of positively charged protons in the nucleus and negatively charged electrons in the energy levels, and neutral particles called neutrons, which are found in the nucleus. Remember also, atoms gain stability by either gaining or losing their electrons. Now, look at these two particles. Now, they come together and develop a mutual force of attraction, which is the bond. Now, you can say that in a unique arrangement, each yellow particle is surrounded by 4 other pink particles. One yellow particle is bonded to 4 other pink particles. So we have that kind of an arrangement. Now, in the same arrangement, each pink particle is surrounded by 4 yellow particles. Each pink particle is bonded to 4 yellow particles. So the arrangement looks like this. Now, what you have on your screen now is the pattern of arrangement. When this pattern is repeated many times over, we form what you have on the screen, and that is what is a structure. It looks very easy, you know. Yes, and it has always been very easy. Let's look at the first type of a bond, and it's the ionic bond. The ionic bond involves the complete transfer of valence electrons from one atom to another or to others. Consider a case where sodium and chlorine atoms combine to form sodium chloride. Sodium requires to lose the single outermost electron to gain stability and form a sodium ion. On the other hand, chlorine atom needs to gain a single electron to gain stability and form a chloride ion. Now, in forming sodium chloride, the electron lost by sodium is gained by chlorine. That electron leaves sodium, forming sodium ion, and it moves and joins the outermost energy level of chlorine, and we have chloride ion. Now, when we have the two particles that are on your screen, the two particles are charged and they carry opposite charges, and therefore they attract each other, they come close together and they form an ionic bond. The same case will happen when magnesium reacts with oxygen to form magnesium oxide. The magnesium ion loses the two outermost electrons, which are then gained by oxygen. Particles now form ions which carry opposite charges. They attract each other and form an ionic. In the formation of ionic bonds, one species loses an electron or electrons to form a positively charged ion or a cation. The other species gains the electron to form a negatively charged ion, which is also called an anion. The positive and the negative particles attract each other, and the electrostatic force that develops between the unlikely charged particles constitute the ionic bond. Now, in general, an ionic bond is a bond formed when there is complete transfer of valency electrons from one atom to the other, culminating to formation of two ions with opposite charges. Metals and nonmetals react to form compounds with ionic bonds. So what happens when magnesium reacts with chlorine? Now, magnesium has two electrons to lose, while chlorine has room for only one electron. Now, in such instances, we shall have two chlorine atoms, each accepting one electron from the magnesium atom. Now, I want you to see that the electrons from magnesium are lost successively and not simultaneously. There is the attraction and you have the ionic bond. How about the reaction between sodium and oxygen? Oxygen need two electrons, but sodium can only donate one. Now, equally, we shall have two sodium atoms reacting with one oxygen atom to form sodium oxide. After forming the ionic bond, what kind of a structure do we expect? Now we look at giant ionic structures. Now we had indicated earlier on when we began that after the formation of a bond, there is a repeated pattern, which when repeated many times over results into a structure. For example, in the sodium chloride structure, many sodium and chloride ions are arranged and packed in regular patterns. Now in this pattern, each sodium ion is surrounded by 6 chloride ions that are equidistant from it. Now equally, each chloride ion is surrounded by 6 sodium ions that are equidistant from it. Now the pattern repeats itself many times over and in all directions, resulting in the formation of a giant ionic structure. Now let us take that arrangement to represent that information. And one sodium particle, the yellow particle, is surrounded by 6 chloride ion particles, the pink one. And then we're going to take one pink particle, it's also surrounded by 6 yellow particles. Now what is formed is a pattern. Now if this pattern repeats many times over, we have that is a structure. So that is what we would expect the structure of sodium chloride to look like. And not just for sodium chloride, most ionic substances are crystalline in nature, and others would include potassium nitrate, sodium iodide, potassium bromide, and calcium nitrate. Let's look at the physical properties of ionic compounds. Now, ionic substances are mostly soluble in water because they are made up of oppositely charged particles. Now, these particles are attracted by the polar molecules of water, and we shall see how that happens shortly. Now, they are mostly insoluble in nonpolar solvents. Ionic compounds have very high melting and boiling points because the ionic bonds are very strong and require a lot of energy to break. Boiling and melting involves the breaking of these bonds, and thus a lot of heat energy is needed. Now, in their solid state, ionic compounds do not conduct electricity. Why? Because the ions forming the substance are not mobile. However, in aqueous or molten state, the ions are mobile within the molten liquid or solution, and thus they conduct electricity. Now, up to that point, we now know other particles that can conduct electricity. Initially, we had said electricity can be conducted by free delocalized electrons, and now we can see free ions can also conduct electricity. And actually, those are the only particles that can conduct electricity and heat, that is delocalized electrons and mobile ions. Now, how exactly does water dissolve ionic compounds? Now, water is polar. Water is a polar molecule. That means its constituent atoms carry a partial charge. For water molecule, the hydrogen is partially positively charged and the oxygen atom is partially negatively charged. So taking that to be sodium chloride, the chlorine and sodium ions are held together by the ionic bond. On the other hand, we have the water molecule. You can see the hydrogen carry a positive charge and the oxygen carry a negative charge. So the chloride ion, being negatively charged, is attracted to the hydrogen atom of water, and sodium, being positively charged, is attracted to the oxygen. Now, in this way, we say sodium chloride has dissociated into constituent ions, and the ions are now free or mobile in the solution, and they are responsible for conduction of electric current. The next type of bond is covalent bonds. Now, this very point, it is important that I point out that the atoms combining need not be of different elements. Actually, atoms of the same element can combine as well. If you consider nonmetals such as chlorine, the atoms do not exist singly. Rather, two atoms combine to form a chlorine molecule, and the same case follows for oxygen and hydrogen. Let us consider a chlorine atom. A chlorine atom requires one electron to attain a stable electron configuration. Now, what happens is that two chlorine atoms come together to form a chlorine molecule. Since both are atoms of the same element, none can lose an electron to the other. So what happens is that there becomes a sort of mutual agreement between the two atoms, and a sharing zone is developed. Each atom donates one electron into the sharing zone. Now we say that two atoms share a pair of electrons donated from each one of them. Now take a look at these two atoms of chlorine. Now they come together and share a pair of electrons. Each chlorine atom donates an electron. Now you realize that this diagram only represents the outermost energy level. And if you consider just one atom at a time, you will see that each has a stable electron arrangement. Now this is what is a chlorine molecule. Each nucleus of the atoms exerts some attraction in the shared pair of electrons. Now this nuclear attraction is what constitutes the covalent bond. The covalent bond formed when two chlorine atoms share a pair of electrons is represented as shown on your screen. A molecule is a group of two or more atoms of the same or different elements covalently bonded. Now, up to this point, it is important, and I'm sure you may have noticed, that a bond is not a physical object, rather is a mutual force of attraction. In ionic bonding, the bond was the mutual force of attraction between oppositely charged particles. As for covalent bond here we have seen, it is the force of attraction exerted by the nucleus on the shared pair of electrons. Now the same scenario will be seen in the formation of a hydrogen molecule. Each hydrogen atom has one proton and one electron. Each requires one electron to attain a stable electron configuration. Now what will happen is that two hydrogen atoms will come together. Each contribute its electron to a shared pair, and a molecule is formed. Now realize a covalent bond is represented by two dots or a single short line. A single covalent bond is formed between a pair of electrons. I repeat, a single covalent bond is formed by a pair of electrons, and it is represented by a short line as indicated. Now, other substances that form covalent bonds include water, most gases, oils, sugar, fats, sulfur, and so many others. Now, you need to notice that a single line represents one pair of shared electrons, and thus one covalent bond. Two lines would represent two pairs of shared electrons, and thus two covalent bonds. Repeat that a single line represents a single covalent bond, which represents a single pair of electrons. Let us see more examples, and we start with oxygen with configuration of 2,6. Now the oxygen atom requires two electrons to gain a stable configuration. What happens is that two atoms come together, each contributes two electrons in a shared pair, and we have an oxygen molecule. Next is nitrogen with a configuration of 2 to 5. Now each nitrogen atom needs 3 electrons to be stable. Now two atoms of nitrogen would come together, each contributing 3 electrons into the shared deal. Now you realize the covalent bonds formed by nitrogen. 6 electrons are in the shared zone, that is 3 pairs, and therefore we have 3 covalent bonds. Let's see water, and water constitutes of hydrogen and oxygen. Both hydrogen and oxygen need to gain electrons to be stable, so none of them desires to lose. Now, however, oxygen needs 2 electrons while hydrogen needs 1. Now, 2 hydrogen atoms combine with 1 oxygen atom such that each hydrogen contributes its electron in a sharing deal. At the end, the oxygen atom will get 2 sharing deals, donating 2 electrons, 1 for each deal with hydrogen atoms. Look at that, and there you have the covalent bonds representing water. Now, while you are drawing these diagrams, you must be aware that the atoms are not of the same size. If you look at this, you realize that the oxygen atoms are actually larger than those of hydrogen, and this must be reflected in your drawing. Don't just draw circles. Next, we look at ammonia. Ammonia is composed of hydrogen and nitrogen. Nitrogen with the configuration of 2,5 needs 3 electrons. Now, hydrogen needs 1 electron. What happens is that 3 hydrogen atoms will combine with 1 nitrogen atom in a sharing deal, just as in water. So there you have the ammonia molecule illustrated. Carbon 4 oxide is a combination of carbon and oxygen. Carbon needs 4 electrons, oxygen needs 2. Now, this is rather tricky, but is also easy. Now, if 2 oxygen atoms combine with 1 carbon atom, each oxygen atom will donate 2 electrons. The carbon atom will also contribute 2 electrons to each sharing zone. Now, in total, carbon will have received 4 electrons it needs. Each oxygen will also have received the 2 electrons it needs in a sharing zone as illustrated here. And there you have the covalent bond for carbon 4 oxide. You realize there are double covalent bonds formed between carbon and each of the oxygen atoms. There is an interesting type of a bond I want us to look at. So let's go back a little and consider the ammonia molecule. Now, in this molecule, if you look at it keenly, you will realize that there is a pair of electrons that never participated in the sharing deals. This is called a lone pair or unshared pair. There it is. Now again, let's rethink a hydrogen atom. Now recall that a hydrogen atom has 1 proton, 1 electron, and no neutron. So if a hydrogen atom loses the only electron it has, what is left is only a proton, since it does not have a neutron. Actually, a hydrogen ion is mainly called a proton because that is what it is. Remember, we said an energy level is not something physical. So the loss of an electron from the atom of hydrogen only leaves a proton. Since a proton is positively charged, the hydrogen ion is represented as shown on your screen. Now, consider a reaction between the hydrogen ion and ammonia molecule. The hydrogen now needs 2 electrons to be stable. It can get them in a sharing deal. But wait, the hydrogen ion has no electrons to share with the ammonia molecule. Now, however, ammonia can be kind enough because it has 2 lone pair of electrons it can share now. hydrogen can combine with ammonia and accept these unshared electrons in its energy shell. So this is what happens. The hydrogen comes and accepts the two unshared pair from ammonia. Now in this combination of ammonia with a proton, the shared pair of electrons were contributed by one of the partners. Hydrogen ion did not contribute any electron. Now this is called a coordinate bond and is represented by an arrow as shown on your screen. Now also note that nitrogen atom is a neutral species with equal number of protons and electrons. Similarly, the first three hydrogen atoms that formed ammonia are neutral, each with one electron and one proton. However, their hydrogen ion had no electrons and was thus positively charged, and therefore it introduces a positive charge with the net effect that the formed molecule has a net positive charge, and we call it an ammonium ion. Another coordinate bond exists in carbon-2 oxide, commonly called carbon monoxide. Now, this molecule has one carbon and one oxygen. A carbon atom has 4 valence electrons and thus needs to gain 4. On the other hand, an oxygen atom has 6 valence electrons and needs to gain 2 more to fill the outermost energy level to make it stable. There will be 2 deals entered here. In the first mutual deal, each atom donates 2 electrons into the sharing zone. However, you notice that oxygen still has a lone pair of electrons. The oxygen atom, in its kindness, donates this pair into the sharing zone to form a coordinate bond. Now the molecule is represented as such. Now, in summary, a coordinate bond is a type of a covalent bond in which a shared pair of electrons are donated by one of the participating partners alone. It is a covalent bond because it involves sharing of electrons. So, just what kind of structures are we looking at in compounds that form covalent bonds? Now, substances with covalent bonds have either a molecular or a giant covalent or atomic structure. We start with molecular structures. Now, in molecular structures, atoms forming a molecule are held together by strong covalent bonds like we've seen. However, one molecule is held to the other by weak van der Waals forces. Get that right and don't lose it. The atoms in a molecule are held together by strong covalent bonds. The molecules are held to each other by weak van der Waals forces. Now, most molecular substances are usually liquids or gases, at least at room temperature. The van der Waals forces hold the molecules in repeating patterns, resulting in a molecular structure. Now, for example, what you have on your screen are very many molecules. Now, each molecule has 2 atoms. Now, the 2 atoms forming a molecule are held together by strong covalent bonds. However, in between the molecules, there is weak van der Waals force. So, the weak van der Waals forces are the intermolecular forces, but covalent bonds are the interatomic forces. Now again, if you look at iodine, you can see iodine is diatomic, that means each molecule is made up of two atoms, again covalently bonded. But each molecule is held to the other by weak van der Waals forces. So let's turn to physical properties of molecular compounds. And molecular substances have low melting and boiling points. Now, although the atoms are held together by strong covalent bonds, the intermolecular forces are weak van der Waals forces. Now, boiling and melting involves breaking of the intermolecular forces. Don't get confused here, because in the ionic compounds, boiling and melting involves breaking of the ionic bond, which is quite tough. However, in molecular compounds, boiling and melting only involves breaking the intermolecular forces, which are the weak van der Waals forces. The molecular compounds are also poor conductors of heat and electricity. Why? Because their structures are composed of molecules and they do not have any delocalized electrons, neither do they have free ions. Remember, we said only free ions or delocalized electrons can conduct electric current. Now, some molecular substances include sulfur, sugar, iodine, fats, paraffin, wax, and naphthalene, and many others. Now, water is also a molecular compound but has something interesting. Now, the intermolecular forces in water are not the weak van der Waals forces, but rather they have what we call hydrogen bonds. A hydrogen bond is an intermolecular force whereby the electropositive atom of one molecule is attracted to an electronegative atom of another molecule. Now, in water, hydrogen is electropositive while oxygen is electronegative. So if you look at that, that is the molecule of water. The water molecule is composed of two hydrogen and one oxygen atom. These are held together by covalent bonds. You can see the hydrogen is electropositive and the oxygen is electronegative. So the negative oxygen exerts some attraction to the positive hydrogen, and this constitutes a hydrogen bond. The van der Waals forces are weak attractions and exist when molecules or atoms are close together. On the other hand, a hydrogen bond is stronger than the van der Waals forces, and this is why water has a higher melting and boiling point than chlorine or even hydrogen sulfide, which have van der Waals forces. Now, this phenomenon is also seen in comparison of ethanol and dimethyl ether. Now, both compounds have the same relative molecular mass of 46. However, ethanol has a higher boiling point of 78.4 compared to dimethyl ether, which has negative 24 degrees Celsius. This is because ethanol has hydrogen bonds as intermolecular forces, while dimethyl ether has the weak van der Waals forces. We have said comparatively, hydrogen bonds are stronger than van der Waals forces. Now, the hydrogen bond is, however, weaker than the covalent bonds. Now, most molecular substances are insoluble in water, but some like sugar, ethanol, and ethanoic acid are soluble due to presence of hydrogen bonds. Next, giant covalent structure, also called giant atomic structure. It is not always that whenever covalent bonds form, a molecular structure will result. Now, in certain instances, the structure is composed of large numbers of atoms covalently bonded, forming repeated patterns that extend in all directions. Examples are diamond, graphite, and silicon 4 oxide. Diamond is an allotrope of carbon. Allotropes are different forms of an element in the same physical state. Now, in the diamond structure, each carbon atom is bonded to 4 other carbon atoms by strong covalent bonds. Now, this forms an octahedral structure. This pattern repeats itself many times over, resulting in a giant atomic structure. All carbon valence electrons are used in covalent bonding. Remember, carbon has 4 valency electrons. So if one carbon bonds to 4 other, it means all the valence electrons have been used up and there is none that remains. There are thus no delocalized electrons, and so diamond is a poor conductor of heat and electricity. All bonds in diamond structure are strong covalent and the atoms are closely packed together. Diamond is thus the hardest known substance with a very high melting point of 3700 degrees Celsius. On the other hand, in graphite, each carbon atom is bonded covalently to 3 other carbon atoms. Now, based on the knowledge that carbon has 4 valence electrons and that in graphite it bonds to 3 other carbon atoms, it means there is an unused electron which is usually delocalized in the graphite structure, and that is why graphite conducts electricity. The structure of graphite consists of layers in which the carbon atoms are held together by strong covalent bonds, forming a hexagonal arrangement. Now, each layer is held to the other by weak van der Waals forces. Now, this makes the layers slide over easily, explaining why graphite is slippery. Remember, van der Waals forces are very weak intermolecular forces. So let's look at the last type of structure, and we look at metallic bond and giant metallic structures. Now here there are many atoms surrounding any one atom in all directions. The valence electrons are thus attracted mutually to many nuclei. This gives a scenario whereby the positive nuclei appear to be immersed in an ocean of electrons. Now, to illustrate this, consider this metallic atom. It has 1 electron in the outermost energy level. It could be potassium, could be sodium, lithium, or any other metal with a valence electron, 1 valence electron. So it will donate this 1 electron into the delocalized region. Now, if so many other atoms do the same, we will have a metallic structure as shown here, whereby the positive nuclei appear to be immersed in a sea of electrons, and these electrons are said to be delocalized. The attraction between the positive nuclei and the negative electrons hold the atoms together in repeating patterns, forming a metallic structure. These electrostatic forces of attraction constitute the metallic bond. Again, there we have defined a bond as a force of attraction. The electrons are delocalized, explaining why metals are good conductors of electricity. Now, the conductivity in metals increases with increase in the number of delocalized electrons. Thus, aluminium with 3 electrons per atom is a better conductor than magnesium, which has 2 delocalized electrons per atom. The metallic bond is a strong one, making metals have very high melting and boiling points. Melting and boiling points increase with decrease in atomic radii, and thus sodium has a higher melting point than potassium. Equally, aluminium has a higher melting point compared to magnesium and sodium. With smaller atomic radii, atoms are densely packed in the structure and thus makes the metallic bond even stronger. Also, large number of delocalized electrons means increased electrostatic attraction and hence an even stronger metallic bond. Well, that's pretty much about it for structure and bonding, but make sure you do not confuse between bonds, structures, and interforces. There are three types of bonds, that is ionic, covalent, and metallic. Under covalent, we have a special bond called coordinate covalent bond. In structures, we have giant covalent, also called giant atomic, seen in diamond and graphite. We have giant metallic, seen in metallic structures, and we also have molecular structures. For intermolecular forces, we have discussed the van der Waals forces and the hydrogen bond. Now, we've said ionic bonds are formed when one species loses an electron or electrons, which is or are then gained by another species, and this is seen in the reaction between metals and nonmetals. It is the electrostatic force of attraction between cations and anions that constitute the ionic bond. Covalent bonds, on the other hand, we've seen occur when two nonmetallic atoms of the same or different elements combine and share electrons to form a molecule. Now, atoms in a molecule are held together by strong covalent bonds, while the intermolecular forces are weak van der Waals forces or hydrogen bonds. Now, a coordinate bond is a covalent bond formed when the shared pair of electrons is only donated by one of the participating partners. The weak van der Waals forces make molecular substances have low boiling and melting points. You and I know that the delocalized electrons or free ions are responsible for conductivity in a substance. In giant covalent structures, the atoms are held to each other by strong covalent bonds, and thus the substances with these structures have very high melting and boiling points, like diamond and graphite. In metallic structures, the positive nuclei appear drawn in a sea of free electrons. The electrostatic forces of attraction between the positive nuclei and the electrons constitute a metallic bond. The pattern repeats many times, forming a metallic structure. Finally, you and I know that the valency electrons are instrumental in determining the type of a bond to be formed.
This is my own and my soul. This is my own. I have a goal. I believe I will succeed in my goal. This is my own.
Islington College.